Hi, this is an example problem on correcting farsightedness. Pause for a moment to read the question. All right, so whenever we're solving problems that have to do with correcting vision, it's important to know some of the terms, including the near point, the far point. So let me jump to a PDF slide that tells us about it. So accommodation range, you can see here. This is the range of distances where your eye, without any corrections, is able to make a focused, clear image. And so you're going to be able to form this on the retina with your own lens. Now, for the furthest object you can make a crisp image with, focused image, is called the far point. And here you're going to relax your lens because you don't want to converge the rays too quickly. The nearest point where you can make a focused image on your retina is called the near point, and here you're going to tense the lens to get as much curvature as possible because you want to converge the rays quickly. Now, for most human beings, everybody's different, of course, but kind of an average, what we call normal range for the accommodation range is the near point. You can see something that's about 25 centimeters from your eyeball. Now you can check this yourself, get a ruler, get something that you write on, you can look at and see, you can check it yourself. As you're younger, you'll have a shorter one perhaps, right? If your eyes not have any correction problems. As you get older, this increases. And for the normal seeing far point for people is you can see to infinity. That means when you look at a star in the sky, if you have a normal far point, it's going to look like a point of light. If you have corrective issues, you're going to see like blurriness or multiple things there. All right, now we're doing farsightedness here. The terminology is kind of backwards. Farsighted means you can't see near. So the idea here with the corrective lens is, okay, here you have an object. It's close. It's closer than the near point. You can't form an image on this because your lens is not able to converge quickly enough the rays so that the image is going to be smeared on your retina. We need to put an additional converging lens in there by the eye, or a contact lens on the eyeball. Gives you additional convergence in addition to your own lens, so that now you can converge that onto that image crisply onto your retina. What this does, the way to think about this, is it produces a virtual image over at your near point. So you're able to see this now, in a sense, because you're seeing an image in your brain, and it's at the position where you are able to see. All right, so how do we do this problem then? Well, we're always going to begin by drawing a principal axis. So let's go ahead and do that. And we're going to go ahead, and I'm going to start by just drawing the eye. So you've got your eyeball here. There it is. And right, it's kind of your pupil. All right, so for all vision problems, what we want to do here is figure out where the object can be placed so that this person can see it in a corrected way, right? So in this case, without glasses, this person, or without contact lenses, this person has a near point of 75 centimeters. We want them to be able to put an object at 25 centimeters and be able to see it. So we're going to go ahead and label this point here. So here is we're going to measure it exactly from the eye. So here's where the eye's at, right? And if we want to go ahead and label a point at 25 centimeters right over here, notice that that's the distance from the eye to where we want to be able to see something. That's where we're going to go ahead and put the object. So let's label this here. This is going to be O, the object. And we know from the eye to the object is 25 centimeters. Now notice we haven't put the lens anywhere yet. Now's the time to do the lens. And in part A, we're going to go ahead and use a contact lens, which goes right on the eye. So this is a converging lens, as we said before. It has this teardrop shape. We're going to stick it right on the eye. And importantly, I want to go ahead and draw the center of the lens where we measure all distances from. So there's our center of the lens. Look at, in this case, the center of the lens coincides exactly with the position of the eye. So when we calculate our object distance, we're going to do it like this. We start from the edge of the lens and we go out to where the object is placed. Okay, cool. That is our object distance. DO is equal to 25 centimeters. Now, as we saw before, the way that this corrective lens corrects the problem of farsightedness is by making the virtual image appear at the location of the patient's near point. So the 25 centimeters, 50, so about at the end of the line here, right? This is going to be the near point. And that's going to be equal to where the image is going to be placed, okay? So the image goes where the near point is. Now to measure that out, what is DI? Again, as usual, start from the edge of the lens out to the point where the image is located. And so this is going to be our image distance, DI, but we need to consider the sign conventions. So this is the front side here where the object is, right there, right? And let's look at the image. Is it going to be positive or negative? Let's remember our sign conventions. So object, DO, front, positive, good. Image location, the image is negative if it's on the same side the front as the object. And it is in this case. Virtual image, same side as the object. That means we need to put a negative sign there. So it's going to be minus 75 centimeters from the lens out to the near point. So we know now we can use the thin lens equation. 1 over f is equal to 1 over do plus 1 over di. And now we can calculate what the focal length of this contact lens needs to be. Let's put in our numbers here. So do is 25 centimeters plus 1 divided by a negative 75 centimeters. That gives us a value, 1 over f is equal to 2.667 times 10 to the minus second. And remember, this is 1 over centimeters. So to calculate f, we've got to take the reciprocal, which is equal to 37.5 centimeters. That's the focal length of the contact lens prescribed to help this person see objects placed at 25 centimeters. Now to calculate the refractive power of the lens, that's a simple equation if you know the focal length, but we need to remember something important. So P, the optical power, has nothing to do with power, other words in physics. It's equal to 1 divided by the focal length, but this has to be in meters. It's just a definition. The focal length must be in meters to give you the power in diopters. So 1 divided by focal length, 37.5. Don't do that. That's centimeters, right? Convert this to meters. 0.375 meters. And that's going to give us a power that's equal to plus 2.67 diopters, which is the same as inverse meters. So when you see this number on glasses and readers and things like that, that's exactly what this means. It's a measure of the converging strength of this lens. The positive sign means it's a converging lens because the focal length is positive. And notice that when you have a shorter focal length, that means a stronger lens. It converges the rays quicker. And so if you're dividing by a smaller number, you get a bigger power in diopters. So the bigger the number is, the more powerful the corrective lens. All right, for part B now, we're going to make a simple change here. It says repeat the problem if the person is prescribed eyeglasses with the corrective lens placed 2 centimeters in front of the eyes. So first of all, I want to say that we're not going to change anything in the drawing except for the position of the lens. We still want the eye to be here, and we still want to put objects 25 centimeters away from the eye, and we still need to produce a virtual image over at the near point from the eye, 75 centimeters. So none of those things are going to change. What is going to change is we're going to move the lens, because now it's not a contact on the eyeball, it's going to be a lens that is a little bit in front of the eye. So pause for a second as I move this. Well, to allow us to see both configurations, I've just copied the previous one, but now notice that with the glasses, we've moved the lens so that it is 2 centimeters in front of the eye. So here's glasses. Of course, this was a contact lens right on the eye. And so now we've got something here where we have a distance between the eye and the contact lens from here to here. That is 2 centimeters. So what do we need to change now as we're dealing with glasses? Well, now we're going to be starting all of the distances, DO, DI, from here, right? From where the edge of the lens is. So that means we got to go in and we need to get rid of these guys, right? Because now the DO is going to be from here. Right? And so it's not actually minus 75. What do we have now? We have 2 fewer centimeters, be minus 73 in that case. And we got to do the same for the object here. I'm going to get rid of this. And so the object now again, just like before, going to start from the lens out to the position where the object is located. There we go. And so in this case, again, what we're going to do is we're going to have to get rid of, change the object distance. Instead of 25, right now it's going from less than that. It's from 20, it's from 0 to, from takeoff 2. There we go. Now we're going to go ahead and redo the calculation here, and we'll get new values here. So again, basically we're just going to take this equation and we're updating the values because for the glasses they were slightly different. So that would be a 23 and a 73. And so that gives us a 1 over f, which is equal to 2.98 times 10 to the minus second inverse centimeters, and an f focal length, which is equal to 33.58 centimeters. So for the glasses, we can see that you actually only need to have a little bit shorter focal length for them to work. And for the power, we can go ahead and calculate that as 1 over f in meters. That's going to be 1 divided by 0.3358 meters, and that gives us of about 2.98 diopters. Again, remember that that is inverse meters. And so that is an example of how to use a converging lens to correct farsightedness.